Hi Chemistry 12, welcome to week 7. We're going to have 3 videos this week. First video is going to be on pH curves and polyprotic acids or bases. The second video will be on buffers, and the third video will be on titrations. This is a list of vocabulary that you should be well versed in by the time we're done this video and the second video. So come on back and check these out when we're done. We'll be touching on each of these terms as we travel through our last week for acids and bases. When we talk about an acid-base reaction, essentially it's known as a neutralization. You may have talked about these in Science 10 or even in Chem 11. And a neutralization reaction is when an acid and a base react to create a salt and water. Salts are ionic compounds, so we've talked about ionic compounds often. And what happens with a particular salt is it gets an anion from an acid and it gets a cation from a base. So with Bronston and Lowry, we know that acids want to donate H's and bases want to accept H's. So this acts as the acid and this acts as the base, and we exchange that H and we get our water. But what happens with the anion and the cation is they join together as well. Remember, sodium was a spectator ion, often chlorine was as well. And so it was never the strong base. It could sometimes, but usually it wasn't a strong base. But you'll see these two ions are going to join together to create this salt. So we're going to move away from our 5-step method of predicting acid-base reactions. Those are more the ionic or net ionic reactions. We're going to go back to our old faves from grade 11, double displacement or double replacement, whatever you want to call them. And this is what's going to happen here is we see that we're switching partners, right? Double replacement, we're switching partners, we're switching partners. So you can see here, if we did a net ionics, if we looked at the ions, it would actually be a 2-step process, but they're adding those 2 steps together and they're showing you the exchange of anions and cations here. So the red are your salts, and we're forming water, 1 or 2 molecules of water. So essentially that's what an acid-base reaction is. And we're going to be able to do something, a technique called titration, and it's a way of finding unknown concentrations and volumes. So let's take a quick look generally at a pH curve, and then we'll move from there. So a pH curve, also known as a titration curve sometimes, it's a graph that shows the continuous change of pH during an acid-base reaction. So if we're looking at a neutralization and we want to map the pH of the solution as it travels through this reaction, we can graph that, and that's called a pH curve or a titration curve. And they have very distinct shapes, and we're going to take a look at some of these pH curves, talk a little bit about the zones or areas in a pH curve and what pH curve can tell us about the acid-base reaction, okay, about the neutralization. So if we take a quick look here, you'll see the first thing you want to note about a pH curve is that the pH is always on the y-axis. So you're going to put your pH on the y-axis, and the volume of titrant. We're going to talk about what a titrant is in a minute. So pH, 0 up to 15, and the volume of your titrant, HCl, over here. We see that we've got kind of a flat and then a very drastic drop, so we're going to talk about that. You can tell what you're starting with in your solution, is your solution an acid or a base, by looking at the level or the number of pH. So this pH is starting up here at 11, so it's a base, okay? So we know it's a base because of the pH. So if we bring that base over here, if it cooperates, we'll bring that base over here, so we know our base has a high pH. And what we're going to do to this solution is we're going to slowly, because we want to neutralize it, we're going to slowly add an acid to it. And as we slowly add an acid to it, it's going to neutralize. And then if we continue to add the volume, it will actually convert into an acid. And so we'll end up in an acid, and we know we're ending up with an acid because look at that pH way down here. So we've talked about the pH scale. We kind of know what the pH scale is, how it works now. We know 7 and below are acids and above 7 are bases. We know the lower you get, the stronger the acid, the higher you get, the stronger the base, okay? Now this one over here, see, pH is on the y-axis, volume is on the x-axis, but here we start with a low pH. So here we're starting with an acid, our solution's an acid, and it's going to neutralize, and you might have guessed it, the neutralization happens right in the middle of that, in this case, a drastic rise or a drastic drop. So a very specific shape to your pH curve. Let's go back a minute and let's see what kind of data would they have to create, or I shouldn't say create, what kind of data would they have to measure in order to figure out how this pH curve looks. And so I think we have to take a step back and let's look at a setup for a titration solution. So if you come back here, and we'll be doing more with titrations a little later, and hopefully I think Mrs. Tate was able to get into the school and get some chemicals, so we might actually have a video of her doing a titration, because it's a really good skill or to have when you move into university. Unfortunately, you guys won't be able to do a titration on your own, but even to watch her do a titration would be a big help, I think. So what we have here is just a couple pieces of material, and we'll look closer at the setup a little later. This is a great video. Sometimes I use it to introduce the technique before we head into the lab to do it. So we'll probably come back and I'll put it as one of our links. If you want to see someone doing a titration, it's a pretty good video to do. So we have a burette here, and our burette, it's a very long glass cylinder. It measures very precise measurements. And so we are going to, if you notice, we have HCl, which is our acid, and we have NH3, which is ammonia, and it's acting as our base. So we will have one of our players, because remember, a titration or a neutralization, you have an acid and you have a base. So we're going to put our acid in this burette, and we're going to put our base solution down here in this Erlenmeyer flask. And what we are going to do is, we've been talking off and on about these indicators, and indicators are chemicals that change their color when they're in acidic solution or a basic solution. So we're going to also include an indicator in here, and that indicator will change color as the pH of this solution changes. And people will be like, why the pH is going to change, Miss Ryan? And the reason why the pH will change is because we're going to add acid to it. So we have our base down here, and it's going to have a pH that's, greater than 7. And we have our acid up here, and we're going to mix them together. That's what an acid-base reaction is. But we can only measure our pH in one spot. We can't measure pH in both spots. So what we're going to do is we're going to put a little pH meter here. And a pH meter is just an electronic device we can use that will rapidly take measurements of pH. We could do this by hand and use pH paper, but that's painstaking. So what this will do is it will every 3 or 4 seconds, it would take a pH measurement. And so that pH meter is going to be key, because that's what's going to collect our data for us. So we have our base down here. We have our acid up here. The acid is called the titrant. Whatever we put in our burette is called the titrant, and we'll use that term, okay? And so when we go back, I just wanted to kind of show you where the numbers were coming. So we have our acid. We're going to add it to a basic solution. And you can flip-flop this, right? You could have your base up here and your acid down here. It doesn't really matter. We have equal concentrations. The pH meter is going to measure the pH. So even before we put any acid in here, it'll measure the pH. And then every, let's say, 2 seconds, as I add acid, it's going to measure the pH. And you guys know that as we add acid, we're adding H3O positives. So right now we have a surplus of OH negative. But as we add the acid, we're going to be adding more H positives. And so remember that balance that has to be kept. As the H positives start to go up and we have more and more and more of it, this basic solution is going to become neutral and then acidic solution. Okay, that's kind of what a titration's talking about. So if we go back to our pH curve, when our pH meter starts its measurements, our NH3 has 11, right? It's got a high pH. It's got lots of OH, more OHs in there than it does H3O positives. But what we're going to do is we're going to slowly add the acid to it. Now, for a while, the acid really doesn't do much. In this section here, this kind of flat section, it's called a buffer zone. And we'll talk more. That's our second topic this week, what buffers are. And the buffer is actually part of the indicator that we put in there. So when we choose an indicator, it's got a buffering system in it. But that buffer, essentially, just like you use the word buffer, if you're buffering from somebody, you're trying to protect them. Well, that buffer is going to protect the pH, and it's going to keep that solution basic as long as it possibly can. But then eventually it just can't handle it anymore. And we see this drastic drop. Look how quickly that pH drops. This is a very key zone on a pH curve. Okay, here it's a drop because we started with a base and we're going to eventually get into an acid because we're adding acid. Here we started an acid, so we have a drastic climb. Okay, but that is a really important spot, because smack dab in the middle of that drop is something called an endpoint or an oh, I have a hard time with that. Equivalence. I want to put the V in there. V is going to be important. Equivalent point. Because something happens right smack in the time. It's when neutralization happens, yes. Here you'll notice it's not, a lot of people assume neutralization happens when the pH is 7. That is true over here in this case, and that tells me something about the acid and base that I'm using. If the neutralization, and that's what's happening right there smack dab in the middle, it's called the endpoint. It's when neutralization occurs. And in this case, if you trace it over, neutralization occurred at 7, and that's what we would predict, right? Strong acid, strong base, they're going to meet in the middle. And when they neutralize, their pH is going to be 7. And that's true. This was a very strong acid. It was down here at 1. It turns into a very strong base up here at 14, almost 13, 14. So when you work with a strong acid and a strong base, you're absolutely right. Neutralization is going to happen very close to 7. But over here, it's a little different. We started with a base, but ammonia, NH4, it's not a very, very strong base. And so what happens here is it's going to neutralize still, but it's a little later, right? It neutralizes, in this case, just trace over. So if you're ever wondering what the pH is when it neutralizes, here it's about 5.5. And the reason why it's below 7 is because we were working with a weak base, but look at this. We created a really strong acid. So we added enough acid to flip the tables, and we have a very strong acid down here, okay? So when you're working with a strong acid and a weak base, your neutralization points can be a little below 7. And I'm sure you guessed it. If you're working with a strong base but a weak acid, your neutralization point, your end point, is going to be a little higher than 7. So we can't bank on it always being 7. That's true if you have a strong acid and a strong base that you're working with. And remember, strength of acid and strength of base are all about ionization. It's not about their concentration. We can't just amp up the concentration and think that the acid and base is stronger now. We've talked about that already. So the strength of acid is just how well it ionizes, nothing to do with its concentration. So what do we mean by neutralization, or what's really happening when you hit this end point, which is in the middle of this drop? What's happening is this. When we have neutralization, the moles of acid equal the moles of base. So they're said to be stoichiometric, 1-to-1 ratio. Moles of acid equals moles of base. Some people have the misconception that it's the volume of acid equals the volume of base, and that is incorrect, okay? Incorrect. It's not the volume that's equal when we reach equilibrium. It's the moles of acid and the moles of base are equal. So stoichiometric, 1-to-1 ratio. That's what happens at this point. That's what happens at this point. So this point, and a lot of people are like, well, why are you calling it an endpoint? It says equivalence point here. We've got to be very careful. When it's the equivalence point, technically, there you want, and that's why I wanted to point out the V in equivalence. Valence, V standing for volume. So the equivalence point is the volume of titrant you had to put in. How much did you have to put in from that burette? Right? In this case, the acid, that's what we put on our x-axis. How much volume are we adding from that burette? How much volume are we adding from that burette? Here, HCl was in the burette, so it's your titrant. Here, NaOH was in the burette, it's your titrant. Okay? Another hint to figure out what's in the burette and what's in the Erlenmeyer flask, it says titration curves for titrating 0.1 moles per liter ammonia with. So when it says titrating with, the afterthought is what's in the burette. So the ammonia is going to be in your Erlenmeyer flask, and we're titrating it with. So whatever the with is what we're putting in the burette. So we're starting with the base, we're putting in the acid. Over here, you'll notice we're starting with the acid and we're titrating with the base. So you can flip-flop it. You just have to be clear on that. So the titrant, the volume of titrant, and this is important to know when you're in class, we'd be making some of these graphs, but we just don't have the chance to do it here. So we've got 0.3 moles per liter is the concentration, but it's a base. So we're adding this. And as we add it, the pH is going up. Here we're adding acid. As we're adding it, the pH is coming down. Okay? When we get to the middle part of this drop, the end point is when you describe the pH at that middle point. The equivalence point is when you measure the volume of titrant at that point. So the volume of HCl used to reach the equivalence point is 20 milliliters. So 20 milliliters of HCl allowed me to neutralize my base. It doesn't mean I neutralize 20 milliliters of base. That's not what it means. It means once I put in 20 milliliters of HCl, the amount of moles of your base and the moles of your HCl were equal to each other. So this was neutralized. Another way you can think of it is this: when you hit the neutralization point, the OHs equal the H3Os, right? Acid is giving an H3O, the OHs were already there. The OHs are higher here. We're adding just enough H3Os to neutralize this, to bring it up so that the OHs and the HCl's are equal. Okay, that's what you can think about. The pH curve is just that. It's just a graph that shows me this process. The process is called titration. It's a neutralization reaction. We're taking acid, we're adding it to a base, we're going to make water, and we're going to make a salt, which will be the anion and cation of your bases. It's a double replacement, not a net ionic reaction. Okay, we're going to take a look at a few other curves and give you a few more important pieces here. So what else can I tell you? Always know where you're starting and where you're finishing. So if it starts low and finishes high, you're starting with an acid and you're putting in the base, right? The volume of your titrant, so what's in the burette, is on the bottom. Your pH is on the y-axis. Your end point is the pH at neutralization. It doesn't have to be 7. Here it's 7 because we have a strong acid and a strong base. Here it's 5.27 because we have a weak base and a strong acid. If it was, let's say, 8.2, we know we have a strong base and a weak acid. The equivalence point is the volume when you reach that neutralization. The volume of titrant, how much of the stuff in the burette you had to add. Okay, so let's see if I've covered what I wanted to. The pH curves for acid-base reactions have characteristic shapes. If the sample is a strong base titrated with a strong acid, the initial pH is high because the sample is a base and no acid has been added yet. The final pH is low because an excess of hydrogen has been added. The reverse is true for a strong acid titrated with a strong base. So you can flip-flop those things. We'll talk more about what buffers are and how they work, but just for now, realize that the flat sections of your curve are indicating that buffering is going on. And for now, buffering is just keeping the pH at a constant value. Okay, so what I mean here is there's two buffer zones. This is a buffer zone, not a really great one, but it's essentially for almost up to 20 milliliters, you've only gone from 11 to 9. So you really haven't changed your pH much. And then boom, once we hit 20 milliliters, we drop right down to 2. So this flat section here and the flat section here are known as buffer zones. And for now, buffer zones are parts of the curve where the pH is essentially staying consistent. pH is essentially staying consistent here, and then boom, it shoots up, and then it basically stays consistent here. So the flat sections are known as buffer sections. The other thing you want to make sure you're okay with is, if you remember here, I said we were going to take a base, and we're going to put our acid up here. So this is our titrant because it's in the burette. Here's our base. We're going to titrate with acid, and we're going to put the volume of this on our x-axis and the pH. So every 2 seconds, our pH meter electronically is going to take a reading, and we're going to know, every 2 seconds what the new pH is. And the pH is going to change because right now we have excess H positives. The OHs are higher. As we add acid, we're adding H3O positives. Eventually, the H3O positive will equal the OH. That's neutralization. That's the drop in the pH curve. That's when the moles of base are equal to the moles of acid. Okay, neutralization has occurred. Now, if we stopped right there, our curve would stop at that drop. But what we do is we see the acid is continued to increase, and this turns into an acid once we add all of our acid. But there's also an indicator in here, and an indicator, because we need to know, there's not magically, we're not measuring this in real time. We're measuring data, but we're going to go and graph it later. So we need to have a visual indication that there is a endpoint, that there is a neutralization happening. And so what we use is an indicator, and we've worked with indicators before. So if we can put a color in here, we could, know if it's base to start or acid to start. So for example, we're starting with our base here. So if we checked our indicator list, and if you have a periodic table, you could check that very quickly. I'm just going to pause for a second and go get my periodic table. I'm back. So if we're taking a look at this pH curve, we notice that it's endpoint of 5.27. So when it reaches equilibrium, when it reaches neutralization, when the acid neutralizes the base, we have a pH of 4.27. So we're wondering what would be the best type of indicator to use there. And so I just checked my indicator chart, and if you paused and went to find yours, the indicator methyl red. Methyl red is red if it's less than 4.8, and it's yellow if it's greater than 6. So if I went over here and I put some methyl red in here, it would be, because this base is a lot higher than 6, so it would turn yellow. So as soon as I put in methyl red, it would turn yellow here, right? So methyl red, let me write methyl red. Oh, come on! I have no patience for this. I'm sorry, guys. Methyl red, which is an indicator, and it's red when it's less than 4.8, and it is yellow if it's greater. So remember how those indicators work, right? And so I kind of cheated. I know that the endpoint is around 5.2. So this would be a good indicator for me to use. So when I first put it in here, I would expect it to be yellow because the pH of a base is greater than 7, so it's definitely greater than 6. But as we add the acid to it, this solution's getting more and more and more and more and more acidic. It's going to have to neutralize first, and then it'll become more and more acidic. So what's going to happen is when we start, I'm going to have a yellow tinge to my solution because these solutions are colorless, right? So I'm going to have a yellow solution. But as I slowly add the acid, I'm looking for the exact moment when that yellow turns red. Because when that yellow turns red, I've gone just past my endpoint, right? And so you could even pick another one. And there's one here where the color is, I found it here, it's chlorophenol green, chlorophenol red. Chlorophenol red turns yellow at 5.2. That would be a good one to use as well. So we find this range, and we need to have our endpoint fall within the range. If it falls within the range, then when we see this change in color, we know that we've hit our endpoint. We know that we've neutralized our solution. Okay, so that's how indicators work. So here's an example. Here we have 3 indicators. that they could have chosen. This indicator, alizarin yellow, it's kind of a reddish color when it's basic, and then it turns yellow when it gets closer down to 7. Here, bromothymol blue, it's blue at about 8, and it transitions to yellow at about 6. And down here, thymol blue, it's yellow at about 2, and it transitions to kind of an orange at 1. So if these were the 3 indicators that you could choose, which one would be the best indicator in order for you to identify when neutralization happened? If you're saying bromothymol blue, you're absolutely correct. Bromothymol blue is going to let you know that when it's blue, you're still basic. When it's yellow, you're acidic. And as it makes that quick transition, and it is quick, you're at 7, which in this case, because we're working with a strong acid and a strong base, would be its neutralization. So the moles of acid would equal the moles of base right at a pH of 7. The equivalence point would be 20 milliliters. So you'd put in 20 milliliters of base to neutralize this acid. Okay? So that's how the indicators work. So if you have, you guys should pause for a second. And if you don't have your indicator, you should find an indicator chart. And when you find your indicator chart, turn back on, and you want to guess what would be the best indicator we could use here. So when you're trying to decide which indicator to use, look for your endpoint. And remember, your endpoint is always smack dab in the that high rise or high drop. And you'll see here, it's about 9, right? It's about 9. That tells me that I had a strong base, okay, and I had a weaker acid. Strong base and a weaker acid. And so it's right here about 9. So if you go to your indicator chart, you're looking for an indicator that changes right around 9 between its 2 colors. And so I might pick thymol blue. It's yellow when it's 8 or below, and it's blue when it's 9.6 or higher. But that's not the only one. You could also use phenolphthalein, and we use that quite a bit, phenolphthalein. Phenolphthalein is colorless below 8.2 and red when it's 10. So there's a couple indicators you can use, but that's how you choose the correct indicator. And remember, an indicator is a chemical that is one color when it's in a basic solution, and it turns a new color if that basic solution turns acidic, which is what's happening in a neutralization. Okay, I'm getting close to my 30-minute mark, so I'm just going to review a couple terms with you. I was hoping to get both pH curves and polyprotic acids done. Not going to happen, so first video is on pH curves, second video will be on polyprotic acids and bases. So here's another pH curve. I'm starting with a base, so this is what's in my Erlenmeyer flask. I am adding HCl, so that's my titrant, so that's in the burette, and I am going to have a buffer zone here. I'm using bromothymol blue, best indicator for this reaction, because the endpoint's smack dab in this drop, which is about 7 here. And so we're moving down, and then we have another buffer zone here. The buffering is due to the indicator, and we'll talk about that a little later. Okay, x-axis, y-axis, general curve. This was a strong acid. This was a strong base titrated with a strong acid. pH endpoint is going to be 7, and the equivalence point is about 24 milliliters. So here's your terms. Endpoint, and you can read each of them. We have equivalence point. Titration is this process. That's what we set it up so we can actually measure the pH over a certain amount of time to see what's happening. So the titration is the real time, and then the pH curve is once we have graphed that material. A titrant is the chemical that we put in the burette. Okay, and we'll talk more about this general rule. The fact that quantitative reactions produce detectable endpoints. So here, there's 1 drop. So we have one endpoint. You have to have this drastic drop to have an endpoint. So there's one quantitative reaction happening here. Here, one drop or one rise. So there's one endpoint. If you count your endpoints, you count your quantitative reactions, and that's what we're going to be doing in the next video. Okay, here, let me see if I can just find one more for you. Oh, look at this one. Isn't this an interesting curve? We start with a base, we finish with an acid. We're titrating, there's acids in our burette. Here's our pH scale, and we have two bumps. All right, and we'll talk about that in the next video. But this has an endpoint up here, so each drop, this one's a little less drastic, but we have a drop here, and we have a drop here. This has an endpoint of 8. This one has an endpoint of 4. The equivalence point is 25. The equivalence point is 50. Here we put our indicator, so we actually will dictate the second quantitative reaction. So 2 endpoints here, 2 quantitative reactions, and we'll talk about why in the next video. Thank you very much.